All right. In this video, we're going to take a look at a little example where we find the matrix corresponding to a certain rotation in R3. So in detail, the problem that we pose ourselves is to find the matrix associated with the linear transformation that we call T, and it will take vectors in R3 to vectors in R3, and it will first rotate by an angle of theta around the z-axis, and then after that rotate by an angle of phi around the x-axis. And the systematic way to solve problems like this is to figure out what your matrix does to the basis vectors I hat, j hat, and k hat. So that's how we'll tackle this problem. Now I'll calculate t of I hat in detail, and then it'll be an exercise to generalize or adapt my calculation to also find j hat and k hat. But of course, it's a good exercise to pause the video right now and try to figure out if you could calculate t of I hat before even looking at the video. Okay, so let's get started on t of I hat. So I hat is the unit vector in the x direction. And now we're going to rotate this in the xy plane, or around the z-axis, by an angle of theta. That's our first step. And to make this a little bit clearer, I will take a top-down perspective and look at this rotation in the xy plane. So we see that we like to figure out the x component and the y component. Well, the x component is of course cosine theta times the length that we started with, which is 1. So the x component of the result will just be cosine theta, and the y component will be sine theta, and the z component will still be 0. So what this is really is the result of rotating I hat by an angle of theta around the z-axis. Let me denote that by r sub z of theta applied to I hat. Now what we'd like to do next is apply our rotation around the x-axis by an angle of phi. So to do that, we'll take a perspective where we look at the z-y plane, because a rotation around the x-axis will not change the x component. So we should take this vector that we constructed and then rotate that in the yz plane. So here's our yz plane, and now we take our vector but project it to the yz plane. So the z component is still 0 and the y component is sine theta. Now this vector we're going to rotate by an angle of phi. And again, we would like to figure out now the y component and the z component. So that means for the y component, we have to multiply this length by cosine phi. So we'll get cosine phi times sine theta. And for the z component, we use sine phi instead. Now the x component is unchanged. And what we calculated here is the application of our linear transformation t was first rotate by theta around the z-axis and then rotate by phi around the x-axis, and we applied that to I hat. So that's the first of our 3 calculations that we need to do to find the matrix. And now I encourage you to pause the video and use this same method to calculate t of j hat and t of k hat. All right, and before I show you the answer, I want to do a little sanity check on what we just did here. So this is the result of rotating a vector that had unit length, was the I hat vector, around some angles. So if I started with a unit vector and rotated some, it should still be a unit vector. So to give us a little bit of confidence that our calculation here made sense, we can calculate, say, the length squared of this vector, which will be the x component squared plus the y component squared plus the z component squared. And indeed, if we use the rule that cosine theta squared plus sine theta squared is equal to 1, and the same for phi, we need to factor the sine theta here, then we see that this is equal to 1. So while this doesn't prove that we did the right thing, it's a good indication that we're on the right way. Okay, now let's take a look at t of j hat and t of k hat. So here is the result. T of j hat is minus sine theta, cosine phi, cosine theta, sine phi, cosine theta, and t of k hat is 0, minus sine phi, cosine phi. So this can be derived exactly analogously to the calculation that I just did before. And now we should recall that the vectors t of I hat, t of j hat, and t of k hat, they will be the columns of the matrix that we're after. So it's a good exercise to check why this was true again. And let's look at the result. So putting everything together, this will be the matrix corresponding to our composite of two rotations. And now I'd like to leave you with an exercise. Which is to find matrices for the following two transformations. So rotation around the z-axis by theta, and call this matrix R sub z of theta, and rotation around the x-axis by phi. So basically, those are the two transformations that we used to make our transformation T. So you should calculate both of those and then calculate their product. Calculate the product of these two matrices, and you should write the rotation around the x-axis on the left and the rotation around the z-axis on the right.